Today, I'm going to introduce another DPC++ example, word counting using MapReduce. This is a part of the DPC++ Tutorial Series. First, I'm going to talk about general decomposition strategies and MapReduce. In general, we need to decompose the original task into smaller pieces so that we can use parallel computing resources to tackle these smaller problems. The first decomposition strategy is divide and conquer. In divide and conquer, we iteratively break the original problem into sub-problems, which will have a smaller scale. And we do that until the sub-problems can fit well on the computation resources provided. A good example of divide and conquer is image processing. So let's say if we want to apply an image filter on the original image, we can break the original image into smaller pieces or tiles and apply the filter on these smaller tiles. In this way, we can break the original problem, which is the whole image, into smaller sub-problems, which is to apply filters on each of the tiles. And once we're able to complete the filtering on each of the smaller tiles, and we accomplish the original task. The other decomposition strategy is scatter and gather. In this situation, we need to send a subset of the original data set into each parallel resource for computation. And after the computation is done, we need to collect the results and combine them so that we can have a final result. So the combination of the partial results is an important step in the scatter and gather process. MapReduce is such a scatter and gather strategy. MapReduce was proposed by Dean and Gimawat in their 2004 paper. This paper talks about a method for processing large data sets with a large number of processors. And because the employer of these authors, Google, has been using a large number of computing clusters to perform searches and other highly parallel processing on large data sets. This is a general approach that can be applied to multiple applications. And MapReduce has two stages, mapping and reduction. In the mapping stage, processors receive input data and produce key value pairs. In the reduction stage, the processors receive such key value pairs, perform reduction on values corresponding to a given key. The efficiency of MapReduce comes from the fact that mapping processors can operate independently. Also, the reduction processors can do the same in the reduction stage. When you have a large number of computers or processors, and these large-scale parallel processing became reality. In this example, we want to show that how we can partition the original problem into smaller ones and perform MapReduce process and get to the final result. Let's assume that the input dataset can be partitioned to 6 parts because we have 6 processors we can perform mapping stage. So we'll map these 6 pieces into those 6 processors. And the mapping can be done using simple hash or other ways so that we can try to evenly distribute these workloads. The computation on the map processors will produce key value pairs. So the keys will be unique to the data, and the keys will be used as indices in the reduction phase. The key value pairs, as we show here, on the M0 processor, there are 3 key value pairs, and the keys are 0, 2, and 3. And the processor M1 produces 1 key value pair, and the key is 1. As you can see that each processor may produce a different number of key and value pairs. These key value pairs will be dispatched to the reduction phase, which will be carried out on the R processors, R0 through R3, those 4 processors. Also, you notice that we are distributing these key value pairs based on the keys. So all the key value pairs where key is 0 will be sent to R0. And then similarly, the key value pairs where key is 1 will be sent to R1, and so on. So each of these reduction processors will compute on the key value pair where the key maps the ID of the processor. And after the reduction phase, and eventually these results will be combined to generate the final result. So as we show here, key in this example are numbers, but in fact, in other applications, key can be of any data type. And the combination, the key value pairs, need to be grouped by keys before reduction can take place. If we use MapReduce to a real-world problem, let's say word counting, we have a large text file which will be partitioned into multiple word groups. And what we can do is to map these word groups into those mapping processors. So the mapping processors are going to count the number of times each word appears and produces key value pairs. So the key here is the unique words, and the value is the number of occurrences that the mapping processor found in the original text file. So the mapping processors will produce a number of key value pairs, and depending on the keys that this processor saw, it will be produce a different number of key value pairs among these different processors. And then the reduction processors will take these key value pairs, and in the scheduling of the MapReduce processors, we will schedule the same keys to the same reduction processor so that the locality can be leveraged. In the reduction processor, these key value pairs will be computed on, and the sum of the word counts for each word will be merged and eventually generate the final number. Next, we're going to take a quick look at how we can implement such a reduction kernel in SYCL language. So what we show here is a typical reduction pattern. As we explained earlier, the reduction phase is where the key value pairs will be merged, will be computed to generate the final result. So what will happen typically is that the reduction process will combine the partial results from each instance of a kernel, and the results will be operated on using some operator, typically AND or multiplication or maximum or minimum. And these reduction phase can go on for several iterations, so that will reduce the number of instances or outstanding numbers to be merged, to be reduced, and to the final result through multiple steps. And the number of steps will be the log of n being the number of partial results that given to the reduction phase. So what we see here is that these reduction operations are basically the same, although the inputs will be different at each stage. And that's how the SYCL language come up with this reduction library to make this reduction kernel design simpler and try to avoid any errors that may occur if a person needs to implement such reduction phase manually. So what we see on the left side is a typical parallel 4 kernel, and this parallel 4 kernel takes a lambda function. Before we define the lambda function, we declare a ND-range variable, and this ND-range variable has a one-dimensional range, and the first number is the number of total work items, and B is the number of work items. So essentially, this ND range will allow this parallel for kernel to go over all the problems in a space, or go through all the instances, and using B as the number of work items in a work group. This reduction keyword and followed by two terms. The first one is the variable that we use to perform the reduction, and the second term is the functor, which defines the operator that the reduction kernel will leverage. So the reduction parenthesis sum, comma, plus bracket, this defines how we're going to be using the reduction library in DPC++. Specifically, we're saying that in the reduction phase, we need to use sum as the variable to collect the partial results, and we're going to perform the plus operator on these input numbers. And then we are defining the lambda function, and we say that this is passing in the variables as values, and also we use this IT as the iteration variable to go through this ND range. And auto parenthesis sum, this is to say that we're going to be using sum as the reduction variable for the accumulation function, since we're using plus. And what we do in the kernel is that we're going to be getting the global ID of this kernel, and we will use that to index a number in the input variable, where this data of I stores the input value to this reduction function for this reduction stage. So we'll accumulate that to sum. In the next iteration, sum will be used as the accumulation variable for the other reduction kernel. So overall, what we do here is we specify that the kernel contains a reduction which combines instances of the sum variables, and we're going to be using the plus operator or functor in the C++ terminology. This reduction library allows an implementation to automatically generate an optimized reduction sequence. The advantages of using reduction library is that we will be able to restrict accesses to the reduction variables during the kernel execution for safety purpose. And using the reduction library, we cannot inspect the intermediate values of the reduction variable, and also we cannot updating the reduction variable using any other functions. So all these will prevent accidental programming errors and enable efficient implementation on different architectures. Now, the reduction library is very simple and it can be applied to certain applications, but it has its own limitations. So far, this reduction library only allows a single reduction variable. So if you want to collect partial results doing reduction on multiple variables, this will not work. Also, the operators or the functors are simple operations, and the supported functors operators are addition, multiplication, maximum, minimum, so those associative operators. And for some architectures like FPGA, parallel 4 may not be well optimized for memory operations.